Hello, today we're going to talk about transformations of exponential functions. And here I just want to kind of remind you of all of the transformations for any function. And this is why I have an F here. For any function, whatever function you're thinking about, transformations are the exact same. So once you learn transformations, you actually can apply them to any function that you wish. And here we're going to be applying them to our exponential function, which has some base and an exponent x. Let's also remind ourselves that an exponential function, if it's a growing one, the base must be a number bigger than 1, and it's going to look something like this. Okay, it's kind of it slowly rises, and then it kind of shoots up really quickly. It has a horizontal asymptote at y is equal to 0, so the function never touches the x-axis, the original one. And the y-intercept is 1, 0, 1. And that comes from the fact that if I make x 0, any base that I have to the exponent 0 will be equal to 1. And that is that's why we've got y-intercept to be 0, 1. Another type of an exponential function, the parent one or the base one, is if the base is a small number, so something between 0 and 1, okay? And let's take a look here and see if a base is between 0 and 1, the function is going to look something like this. So same idea, except it's decreasing now. It still has a horizontal asymptote at y is equal to 0, and it still has a y-intercept at 0, 1. Okay, but the base here is a number smaller than 1. So let's say it's 1/2 to the exponent x, and over here on the top, it's something bigger than 1, so it could be something like 2 to the exponent x. The x must be in an exponent. That's what makes these functions exponential. X has to be in the exponent. Now let's go ahead and review these transformations. So again, the transformations are going to do to the exponential function the same thing they would do to any other function. So the letter A here, the very front number, always does the same thing. And if you remember from previous units, it's a vertical stretch or compression. The C value at the very end, it's color-coded red because it also does something vertically. It moves things up or down. So that's a vertical shift. So let's go ahead and write down the A. It's a stretch if A is bigger than 1, a vertical stretch. If A is between 0 and 1, so maybe 0.5 or 0.9 or 7/10, it's a vertical compression by a factor of whatever A is. And then if there's a negative in front of the A, so that would make A negative. If there's a minus, the minus would actually flip it, okay? Flip it on the x-axis. So we call that a vertical reflection. If I flip something on the x-axis, this here will be the x-axis. If I flip it, so let's say my function looks like this, and then I flip it to look like that, or I reflect it on the x-axis, we call that a vertical reflection on the x-axis. So that's what the A value will do, all right? The C value, again, it's a vertical shift up or down. If C is bigger than 0, you're going to move up. If C is less than 0, you're going to move down. So easy breezy, makes sense. All of these guys make sense. They should. K and D are just terrible. They're the opposite of what makes sense. They're essentially the other way around. If K is a big number, you would think, well, that's just going to be a stretch. Well, it's not. It's a compression. And because it's together with the x, so I have it color-coded here in blue, it's a horizontal compression. So this is everything affecting the x coordinate. So a horizontal compression, if D is a negative number, you will think, well, it's going to move left or right, but it's actually right. So it's the opposite of what you think. So if D is a bigger than 0 number, you're going to move to the left. If D is negative, so if it's -4, you're going to move to the right. So it just sucks. Like it's totally the opposite of what you think. I usually remember it by saying x lies, okay? So if it's lying, if it's a negative, you're going to move to the right, and if it's a positive, you're going to move to the left. And then similarly with the K, I started talking about it. If K is a big number, you would think, well, that's kind of like a stretch, because that's what happens when A is big. I get a vertical stretch. But when K is a big number, it's actually a horizontal compression, and it's not even by K, it's by a factor of 1/K, and it's a horizontal stretch if K is between 0 and 1. Horizontal stretch, if I look at my original exponential function, let's say it's a growing one, a horizontal stretch would just means that this function is moving, it's stretched out horizontally, so it'll just end up being a lot it'll rise up slower. And if it's a horizontal compression, it's going to be the opposite. You're going to be moving it in, all right? So it's going to rise up quicker. Now, it's a horizontal compression, and it's always by a factor of 1 over k. I kind of remember that by, again, saying that x lies. So here we were multiplying by k, but in order to actually see what it does, we have to divide by k, which is the same as multiplying by 1 over k. Another way I like to remember it, and this is, I mean, I don't like to remember it like this, but this is why the transformations occur in such a way. In order to talk about the vertical transformations, the A and C, Y is already isolated. So I hope that you appreciate that. Y is already on its own, and we're just talking about what A and C do. Now for K and D, they're actually not isolated from the X, right? So if we wanted to really isolate and have X equals something to talk about transformations, I would have to move the D to the other side, so it would actually become the opposite sign. And I would also have to move the K to the other side, and then I would end up dividing by K, which again is the same thing as multiplying by 1 over K. And this is really the reason why the transformations in the X direction, the horizontal transformations, why they end up being the opposite of what you would think. And this is why I just say, well, X just lies, all right? Now, if the K value has a minus in front of it, you're going to have a reflection on the y-axis. So again, if I had a horizontal function that looked like this, and I had my y-axis here and x-axis here, the reflection on the y-axis would just mean that the function would look like this. So it would just basically flip on the y-axis. Okay, so that's if the K value is negative. Now let's go ahead and put these transformations to work. So let's actually look at a transformation, and that's 3 to the exponent x. And let's go ahead and try and apply these transformations to 3 to the exponent x. What would it look like? So let's go ahead and write down 3 to the exponent x. And A is the leading coefficient, so that's going to stay at the front. Why wouldn't it? It's going to stay at the very front of the function. K and D are together with the x. Therefore, they're going to be in the exponent because exponential functions have an x in the exponent. And then C is just going to be added at the end of the function. So the exponential function will look like this. So A is going to be at the front. We put the base that we started with, the 3, in a bracket, just so it doesn't get confused with the A. And again, this base here, it's not a transformation. Not a transformation. Sometimes people will say, oh, what transformation? What does the 3 do? It doesn't do anything. It's actually your base function. It guides what the original function looks like. So if I have 3 to the x, it's just going to rise faster than 2 to the exponent x would look like, right? So if this is 3 to the exponent x, it's rising faster than 2 to the exponent x. This might be y is equal to 2 to the exponent x. So the base function gives us the original function, and then we apply the transformations to it. A, K, D, and C. So that's really what it looks like. K and D are going to start up at the top. So now what if I gave you a function? What if I gave you, so here I'm giving you a function, dang, and it's got a lot of transformations. First of all, you should recognize what's the base function, and you should recognize that, hey, once you strip away all the transformations, if you want to have just a base and an exponent, the base would be 3 and the exponent would be x. So that's what we start off with. That's the parent function. That's the original function. And we're going to go about applying all these transformations. So if I start from left to right, the negative at the very front, what is that going to do? Well, that's going to reflect on the x-axis. That's a vertical reflection. It's part of the A value. So it's a reflection on the x-axis. The 1/2 is going to vertically compress it by a factor of 1 over 2. The K, it's a 4 right now. K is going to be a horizontal. You would think it's a stretch, but it's not. It's a horizontal compression by a factor of 1 over 4. Again, because everything that we do with K, you gotta flip it. So if it's 4, you're gonna make it 1 over 4. And if you think it's gonna, if it's a large number, larger than 1, it's gonna compress it horizontally. D is equal to, it's actually -2. D is equal to -2. That's going to move it to the right, horizontal shift 2 units. And then C is equal to 1. That's a vertical shift up 1 unit. Now, it also is worthwhile noting that the original function, so let's graph the original function, 3 to the exponent x. It has a horizontal asymptote at y is equal to 0. Now, which parameter, A, K, D, or C, do you think would affect the horizontal asymptote? Think about it for a second. The stretches and compressions, the A and the K, they will not, because if you stretch this asymptote, whichever way you stretch it, it's still going to look the same. The D value moves things left or right. So if I move the asymptote to the left or to the right, it's still going to be this imaginary line along the same y is equal to 0 line. So the only thing that's actually going to affect this horizontal asymptote is moving it up or down. So the C value, which is a vertical shift, actually guides what the asymptote is. It's because the original asymptote is that y is equal to 0. The C value here guides the asymptote either up or down. So that's the only thing that's going to move the asymptote, and that actually gives us the equation. This is the asymptote. The horizontal asymptote, of course. So this is, if you know what C is, you actually know what the horizontal asymptote is, right? So let's go ahead and move on to sketching. So to sketch functions, we use what's called mapping notation, okay? And mapping notation is really a way to see what happens to each individual coordinate. So if I start off with X and Y as my original coordinate, and here the X and the Y are the original coordinates, they're all both going to get affected by K and D for the X coordinate and A and C for the Y coordinate, because K and D are horizontal transformations and A and C are vertical transformations. So if I start off with a point, let's say 2, 8, that's my coordinate, that's the original coordinate. And then I am applying a bunch of transformations, and dang, there's a lot of transformations here. A is -1/2, so this is my A, this is my K, this is my D, and this is my C, right? So if I am going to apply all of these transformations, I can say that, hey, the original coordinate was X, Y, and that's going to get transformed into, and we said it's going to get transformed into X divided by K minus D for X, and then the Y coordinate is going to become AY plus C. So before I actually try to figure stuff out, what I like to do is I like to replace my K, D, A, and C with values. So basically, what are my transformations? So let's see. So my transformations are K. What's my K? Let's see. K is equal to, well, it's 4. So I'm just going to make that into a 4. The D value, what's the D? It's -2. So what does that mean? What would I have to replace D with? Well, it should be -2, right? Well, actually, it's not -2. It's going to be +2 because I'm actually moving to the right, right? So it's going to be +2. So the original X coordinate, whatever it is, in order to transform it, I'll have to divide it by 4 and add 2 to it. And if I had more than just one coordinate, if I had a bunch of X and Y coordinates, each X coordinate would get affected the same way. Now, what's my A value? I'm going to replace A with a number, and A is -1/2. So let's go ahead and replace that. A becomes -1/2. And then the C coordinate, what can I replace the C with? Well, that's going to become +1. And that's awesome. Let me just get my marker, so +1. So what's going to happen to our coordinate 2, 8? Well, the 2 is going to get divided by 4. And then we're going to add 2 to it. And the 8, well, we're going to have to multiply it by -1/2. And then we're going to add 1. So what does this become? And sometimes I like to do this on the side. So I'm going to put this on the side right here, on the side of my paper, because I don't really want to take up space. If I had other coordinates, I would really want to keep things lined up. So 2/4 plus 2. What is that? What's my new X? Okay, so this is my new X. 2/4, I can really simplify that into 1/2. And then the 2, well, I mean, 2 plus 1/2, well, that's really just 2.5 or 2.5, right? So that's relatively straightforward, 2.5, comma. So that's my new X coordinate. It used to be 2, but now it's become 2.5, 2.5. Now, what about my new Y coordinate? So let me just change this to my new Y. I'm going to erase my X stuff. So the new Y will become new Y. So it's going to become -1/2 times whatever the original Y was plus 1. And that original Y was 8, right? I told you that. I told you the original coordinate is 8 plus 1. And then I'm just going to do the multiplication here. So what's -1/2 times 8? 8 is really 8/1. And if I multiply fractions, I'm going to multiply the 2 numerators together and the 2 denominators together. So I'll get -8. -8 over 2 times 1, which is 2, right? So negative 8 over 2 plus 1. Well, negative 8 over 2, well, that's just negative 4. And then the plus 1 stays a plus 1. Negative 4 plus 1 is really negative 3. So that really becomes my new coordinate, negative 3 here. So I went from 2 comma 8 as my coordinate into 2.5 comma negative 3. So that's my new coordinate. So that is what the new coordinate becomes. I hope you enjoyed that. Now, the reason why I say this is because when we want to sketch a function, really what you want to do is you want to be able to say, well, what is my original function? So let's say the original function is 2 to the exponent x. You should know the original coordinates of 2 to the exponent x. And I would suggest that maybe you have 3 different coordinates, because you know what the pattern is. You know that the exponential function either looks like this if the base is bigger than 1, or it's a decreasing one and it looks like this if the base is between 0 and 1. You also know a horizontal asymptote is a y is equal to 0 for both of them. So the 3 coordinates that I would like to do is maybe negative 1 for x, 0 for x, and 1 for x. If x is negative 1 and I put it in this original function, 2 to the exponent negative 1 becomes 1 over 2, so that becomes 0.5. If I make x 0, y becomes 1, because 2 to the exponent 0 is just 1. If I make x 1, it'll just become 2, the y value, right? If I replace x with 1. So if these are my original coordinates, I can now transform them based on whatever the transformations are. And here I've got several transformations. And then I like to write down x over k, and then I'll just replace k with a number, and then it's minus d. So if I have negative 2, this will be plus 2, like we said before. So that's going to happen to every single x. I'm going to divide it by 4, and then I'll add 2. And for every single y, I'm going to multiply it by 1/2, and then I'm going to add c to it, which is plus 1. So I'm really just following this mapping notation, we call it, x over k minus d, and ay plus c. So that's what's going to happen to every single coordinate. So let's go ahead and see. So my x coordinate, I'm going to do all the x's first here. So if x is negative 1, it's really going to be negative 1 divided by 4 plus 2. So negative 1 divided by 4, well, that's just negative 1/4. And then negative 1/4 plus 2, well, that's just 1.75, right? So I'm just going to make that into 1.75. That's my x. Now, what if I go to the next x? So I'm going to say, well, x is 0. So if x is 0, I'm going to replace in my mapping notation x with 0. So it'll be 0 divided by 4, which is 0, plus 2 is just 2. So that's what's going to be my x here. And then the next one, my x is 1. So if I replace x with 1, I'll get 1/4 plus 2. Well, that's just 2 1/4, which is really 2.25. So those are my new x coordinates. Now let's do the exact same thing with y coordinates. So each one of the original y coordinates, let's multiply it by negative 1/2. So let's start off with 0.5. 0.5 is the same thing as 1 over 2, right? That's the same thing. So let's replace it. So what do I get? I'm going to do it on the side here. My pooch is in the background saying the video's taking too long. So if I multiply 1/2 with negative 1/2, because that's really what my mapping notation told me, I would also have to add 1. So that'll become negative 1/4 plus 1. And that really becomes 0.75. So that's my new y coordinate here. Awesome. How about if y was 1? So if y was really 1, I would have to multiply it by negative 1/2 and add 1, because that's what I have to do to every single y. So 1 times negative 1/2, that's still negative 1/2. And then I'm going to add 1 to it. Negative 1/2 plus 1, well, that's just 1/2. So that's just 0.5. So that's the next y coordinate. And then finally, I'm going to replace y with 2. So over here, I'm going to replace in my mapping notation y, I'm going to replace with 2. And it'll be 2 times negative 1/2. So I'm going to do that on the side here. Negative 1/2 times 2. Well, that's just negative 1 plus 1. Awesome. That's 0. Awesome. So now I have my 3 new coordinates based on this mapping notation. I love it. I know exactly what they look like. And the only other thing I want to know is where is my asymptote, right? Like, where's that horizontal asymptote? If I can sketch that, I'm in business. And remember what I said, horizontal asymptote is your C value, because it's affected by the movement up or down, right? So by up and down movement of the function. The up and down movement is plus 1. So really, therefore, the horizontal asymptote is equal to y is equal to 1. So now if I go about sketching this function, I know what my coordinates are. So I'm going to have 1, 2, 3, and same thing here, 1, 2, 3. And really what I need is my horizontal asymptote at y is equal to 1. So I'm going to sketch that first. There it is. And then I'm going to sketch my function, my points. I have 1.75. So 1.75 for x, which is over here somewhere. And I got to go to 0.75. So that's over here, 0.75. So that's my first coordinate. The next one will be 2 and 0.5. So 2 and 0.5 will be right there. And then I have 2.25 and 0. So that's right here. And you're going to say, well, Claudia, like, what does this look like? How do I know what this looks like? You should know that the exponential function has that smooth shape. And there it is. It's just like this, right? And that should kind of make sense because the original function, what did we do? Well, we flipped it or reflected it on the x-axis, and then we horizontally compressed it, and we moved it around based on these other transformations. But this should make sense, right? Like the points look like really squeezed in, and that's because they were horizontally compressed, so they're closer together. And the function has